Here we have an easy page of notes that uses the mathematical relationships between our variables to very quickly give us an equation for the relationship between voltage and electric field in a new and more generalized mathematical way. So what we're looking at here is some equations we're very familiar with, I hope, at this point. The fact that delta U is always, whether it's mechanics or not, equal to negative the work done by the field. So that should be fine, I hope. Work done if the force is not constant, or even if it is constant in the most general sense, is integral f dot dx. So hopefully that is okay. We are looking at electrostatics, so F equals QE is not based on E being constant. F equals QE is true generally, even if the electric field is not constant. So then we have the fact that delta V, by definition, is delta U on Q. We, of course, lose the Q's, and we have delta V equals negative integral E dot dx, and we knew all along, right, that delta V equals ed, so that makes sense, right? The electric field is the electric field. The integral of dx is x, so if E is constant, E would come out of the integral. So this is if constant. And if it's constant, then delta V equals ed. So it all makes sense. The negative, of course, is just making sure that our delta V is a voltage drop if we are going against the electric field, and will be positive if we're going with the electric field, and the Q's all have to be put in. So really this is more about the magnitude. We haven't been drawing in magnitude, but magnitude of the voltage change based on the electric field. Well, if we just continue this mathematically, we see that delta V, right, is V final minus V initial. Final minus initial. It's arbitrary. Delta V is the only thing that has meaning since V initial equals 0, since it's arbitrary. And that is really because only delta V has meaning. Okay, so that gives us our integral for the voltage expression. V is a function of x equals negative the integral E dot dx. And look here, by the fundamental theorem of integral calculus, we get that the electric field equals negative the derivative of the voltage with respect to position times x. So this will explain to us on our next page, 2 pages of notes, this equation will explain to us exactly why it is that the electric field has to be perpendicular to those equipotential lines. So the fact that that is perpendicular. So this equation explains this, and we will see why in our next pages of notes.